Hello again. Now we are going to talk about, last time we talked about finding a particular solution of non-homogeneous equations using the method of undetermined coefficients. And basically what we did is looking at the function vt. So again, we have a non-homogeneous equation. So first we find y sub h, which is the general solution of the corresponding homogeneous equation. Then y sub p, particular solution. So we write our solution as y sub h plus y sub p. And to find this particular solution, we use the form of the function b to guess if the function b is of a certain form. We guess the general form of the particular solution and plug it in the equation to find the unknown coefficients. So the main thing in this method is this guessing part. How do we guess the general form of the particular solution? So now we are going to introduce another method to make the correct guess. What we did before in the previous video, that works as long as you guess the correct form of the particular solution. What I am going to introduce today works all the time. So what we do is we use differential operators. And what is called annihilators. Annihilators, yes. So what is a differential operator? This is the usual differentiation. You can think of a differential operator as a differential equation. Think about it as a new notation, a new way to denote differential equations. So first, we denote taking the derivatives operation by the letter D. You may have done this in calculus sometime. So maybe you're not unfamiliar with this notation. So for a function, say f of t of function of t, df of t means derivative of f with respect to t. We can also consider higher derivatives, higher order derivatives. say d squared of f is the second derivative of f with respect to t. And in this way, any natural number k, d to the k means the kth derivative of f. So these are d and powers of d are special type of differential operators. You can also consider taking a linear combination of these operators. We can also consider linear combinations. We are going to denote this linear combination by L of D. L comes from linear because we consider linear combinations. Since we are going to use it to denote differential equations, the highest order derivative is going to have coefficient 1, and then plus a1 times dn minus 1 plus up to a1 by what is LD of f of t? You just apply these operators to f of t. And the last one, a sub 1, since it has no, there is no d in it, it means we are not taking the derivative, we are just using the function f. And here the coefficients a1, a2, oops, the last one should be an. a1, a2, up to an, they are real constants. For example, if you have, say, d squared plus 2d, let's say, plus 2d minus 5, this means, when you apply it to function f, this means the second derivative of f plus 2 times the first derivative of f minus 5 times the function f. Okay, so such a combination LD is called a differential operator. And a non-homogeneous equation, say y n plus a1 n minus first derivative of y plus up to a n of y equals b of t, can be written as LD of y equals b of t, where LD is dn plus a1 dn minus 1 up to an. In this notation, we can also, we can write the characteristic equation. Remember, we have the characteristic equation of the homogeneous equation. So corresponding homogeneous equation is LD of y equal to 0. Characteristic equation P of lambda is the same polynomial as the polynomial LD, but instead of D, we consider the variable lambda. So if a characteristic equation P of lambda, which is L of lambda, equal to 0, of course, this is the characteristic equation. Now, if the characteristic equation has roots lambda 1, lambda 2, up to lambda n, and this is always true. Some of the lambdas may be the same. You may have some repeated root, or you may have some complex roots, but you will always have n roots. This means we can write the polynomial P lambda in the form lambda minus lambda 1, lambda minus lambda 2, lambda minus lambda n. So we can do the same thing to the polynomial LD. We can write the polynomial LD as d, d minus lambda 1, d minus lambda 2, d minus lambda n. Now, what we do now, so differential operator is just a polynomial in the differentiation operator D. Now, what is an annihilator? Consider the homogeneous equation, LD of y equal to 0. So you can think of this equation as you have this polynomial LD in terms of differentiation, and when you apply it to a function, you obtain 0. So basically, okay, so now we consider the problem from the other direction. Given a function, so in solving the differential equation, we are given the equation, we are trying to find a function. And now consider the reverse problem. Given a function, f of t, we try to find a differential operator so that when we apply it to the function f, we get 0. So given a function f of t, a differential operator LD is called the annihilator of the function f of t if, when we apply the operator to the function f, we get 0. And we also want to do this in the most economical way, of course. And if LD has smallest degree, among all such operators. Okay, so quick example. If your function is e to the t, if your function is e to the t, then its derivative is again e to the t. So d minus 1 of e to the t is going to be 0, right? Because d minus 1 of e to the t is going to be d of e to the t minus e to the t. E to the t, derivative of e to the t is itself, so that's 0. And it has degree 1, so annihilator of e to the t should be d minus 1. So what we mean by smallest degree, because once you obtain an operator which annihilates a function, then you can multiply it with any other operator. When I say multiply, I mean take the composition. For example, d minus 1 of e to the t, then d times d minus 1 of e to the t is also 0. Now, what is d times d minus 1? This is, of course, usual polynomial multiplication, d squared minus d. So d squared minus d of e to the t, it means the second derivative of e to the t minus the first derivative. But that's just, again, e to the t minus e to the t, which is 0. So once you obtain an operator which annihilates a function, you can multiply it with any other operator. It will still annihilate the function. Because in the multiplication, you can think of the multiplication as applying d minus 1 first, and then applying d. But once you apply d minus 1, you get 0. So derivative of 0 is again 0. You can think of the multiplication as composition. So if you just put your condition to be the differential operator annihilates the function, there are going to be infinitely many such operators. So we want the one with the smallest degree. So annihilator of e to the t is d minus 1. Okay, not d squared minus d, for example. We want the one with the smallest degree. Okay, now annihilators, how do we find annihilators of functions? Or, okay, the question is, can we always find an annihilator for any function? And so let's say this is example 1. Example 2, the answer is no. For example, the function 1 over t has no annihilators. You see, for the function e to the t, the derivative is itself. So you can find out a polynomial. So take the derivative minus the function, it is 0. But for 1 over t, the derivatives, so if you start with 1 over t and take the derivatives, the first derivative minus 1 over t squared, second derivative 2 over t cubed. Let me say its derivatives. Then the third derivative minus 6 over t to the 4. So when you keep taking derivatives of 1 over t, the power in the denominator keeps getting larger and larger. So you cannot find any polynomial, any linear combination of these derivatives to be 0, because these are all, its derivatives are all independent. Independent. You cannot take a linear combination to be 0. With e to the t, its derivative is itself again. So the function and its derivative are the same. They are not independent. They are dependent. They are the same. But with 1 over t, all the derivatives are independent, so you cannot find any annihilator. Another example would be sine t, for example, trigonometric function. Its derivative is cosine, and the second derivative is minus sine, right? So the first derivative, yes, different, but the second derivative is a negative of the function. So when you take the differential operator, d squared plus 1, right? The second derivative plus the function of sine t, this is 0. So annihilator of sine t is d squared minus 1. There is no first order annihilator of sine t, because the first derivative of sine t is cosine t. It is independent from sine t, but the second derivative is again sine t. Similarly, d squared plus 1 of cosine t is also 0. The annihilator of cosine t is also d squared plus 1. In this reverse problem, you can think of it in this way. Remember, we considered homogeneous equations, and we looked at the characteristic equation. Depending on the roots of the characteristic equation, we obtained solutions. So once you have a solution of a homogeneous linear equation with constant coefficients, that means that solution function has an annihilator, right? Okay, let me write out what I mean. For a linear homogeneous ordinary differential equation with constant coefficients, so remember, we can write such equations as LD of y, sum LD of y equal to 0. The solutions y1, yn are annihilated by LD. Because LD, since they are solutions, LD of y1 is 0, LD of y2 is 0, LD of yn is 0. So when you're trying to find annihilator of a function, you can think of it this way. Is your function a solution of linear homogeneous ordinary differential equation with constant coefficients? If it is, what kind of an equation? So depending on our experience with homogeneous linear equations with constant coefficients, I want to give you a list of some functions and their annihilators. Okay, so the basic solution, the function we see most in solutions, exponential function, e to the power a t. So if you consider our example 1, the derivative is a times the function. So when you take d minus a, it annihilates the exponential function. Oh, maybe, okay, let me go back and give a quick example for if your function is a polynomial function, say t to the power k. Now, when you have k is a natural number, so when you take the first derivative, it's k times t to the k minus 1, second derivative t to the k minus 2, and so on. So when you take the k plus first derivative, it is going to be 0. The kth derivative is going to be k factorial, constant. So k plus first derivative is going to be 0. Think of t squared. The first derivative is 2t, second derivative is 2, so third derivative is 0. So annihilator of t to the k is d to the k plus 1. So we can write it, we can add it to our list here. Annihilator of t to the k is d to the k plus 1. Annihilator of sine bt, let's say, cosine bt. In example 3, I did sine t. If you have a coefficient in front of t, then you would get the first derivative, you have the coefficient b, and in the second derivative, you have the coefficient b squared. So instead of taking d squared plus 1, you should take d squared plus b squared. Okay, now what about a combination? What if we multiply these functions? So if you multiply t to the some power of t with the exponential. Now, such solutions, if you remember back to linear homogeneous equations again, they occur when you have a repeated root, right? For a repeated root, if lambda equals a is a repeated root, the independent solutions are e to the at, t times e to the at, t squared, t cubed, and you go up to t to the k if a is a repeated root. So you have b minus a to the power k plus 1. Let me check, yes, right? So if you have this differential operator, d minus a to the k plus 1, its characteristic equation is going to be lambda minus a to the k plus 1. So lambda equals a is a root with multiplicity k plus 1. So you get solutions when you multiply e to the at with powers of t going up to power k. Okay, what if you multiply the exponential with the sine or cosine? So e to the at times sine bt, or e to the at cosine of bt. Again, so let me sorry. Again, if you think back to linear homogeneous equations, such a function is annihilated. You get such a function as a solution when you have complex roots, remember? So the number a in the exponential function is the real part of your complex root, and the number b in your function is the imaginary part of your complex root. So, but when you have a complex root, it means its conjugate, complex conjugate, is also a root. So when you think of it this way, your characteristic equation is going to have lambda minus that complex number, and also lambda minus the conjugate of the complex number as factors. And when you multiply them out, you get the operator d squared. You need a second order operator because you have two roots. For a complex root, you have the corresponding conjugate also as a root, so it is second order, minus 2a times d, and the constant term is a squared plus b squared. This is going to be your annihilator. Okay, now we may multiply these with a polynomial. So t to the k e to the at sine bt, or t to the k e to the at cosine bt. So this means, if you look back to our examples, I'm pretty sure I solved an example when you have a complex root as a repeated root. So in this case, we have a complex root because we have exponential and sine and cosine, so that means complex root. Multiplying with t to the k means the root is repeated k plus 1 times. So basically, you get the same polynomial as above, and take it to the power k plus 1, because you need your complex number as a repeated root. So you can refer back to this list whenever necessary, but you can come up with this annihilator yourself, as I said, when you think of which linear homogeneous ordinary differential equation has this function as a solution. And this list is a complete list. No other functions, no other types of functions are, no other type of function has an annihilator. So other trigonometric functions, for example, tangent, cotangent, secant, cosecant, when you keep taking derivatives, the derivatives keep getting more complicated. They are independent from each other, so you cannot find any annihilator. Same thing with the square roots. As we have seen in example 2, rational functions, the derivatives keep getting complicated, so they don't have annihilators. The only type of functions which have annihilators are the functions in this list. So if, for a non-homogeneous equation, if your function, bt, on the right side of your equation is one of the functions in this list, or a linear combination of these functions, then we can use the method of undetermined coefficients because they have annihilators. Okay, now, how do we use these annihilators to find this particular solution? So we use this little fact, this little note. If you have two functions with two annihilators, so if the operator LD annihilates the function f, and say another operator, say MD, annihilates the function G, then when you multiply them, it annihilates f plus g. Because when you apply it to f, first of all, the product, the order of the product is not important. So when you apply it to f, you first apply LD, you get 0, and then you apply M, it is 0. Plus, when you apply it to g, differentiation is a linear operator, so for the sum of two functions, you can distribute. When you apply it to G, when you apply M, you get 0. So afterwards, when you apply L, it is still 0. But instead of taking the product, we can take least common multiple of LB and MD. Let me show this in an example. Find the annihilator of the function e to the minus 2t plus t squared e to the minus 2t plus cosine of square root of 3t plus t. Okay, annihilator of for e to the minus 2t, we consider the linear homogeneous equation whose root is minus 2. So the operator is d plus 2. For t squared e to the minus 2t, again, lambda equals minus 2 is a root with multiplicity 3 in order to get t squared. So we have d plus 2 cubed. For cosine of square root of 3t, we have complex root I times root 3. So that means the polynomial is d squared plus 3. And for t, first derivative is 1, second derivative is 0. D squared t is 0. Okay? So we need the least common multiple of d plus 2, d plus 2 cubed, d squared plus 3, and d squared is, so if you multiply all of them, you have d plus 2 to the 4, but you don't need the power 4. The power 3 works. So when you apply the power 3 to the function e to the minus 2t, the first d plus 2 is going to kill it anyhow. So the other powers of d plus 2 will still give you 0. And when you apply it to t squared e to the minus 2t, you get 0. And the others will kill the other functions. So this is the annihilator. Okay, now I need to stop now. So that means in order to talk about how to use annihilators to obtain the particular solutions, we are going to do it in the next video. So this is, I guess, the first part of lecture 15 then. Okay, that's all for now.